Thank you for the nice introduction and welcome to our participants in this webinar today. Let us kick off with today's topic, Helmut. What does material characterization look like in the field of plastics?
Yeah, David, basically the characterization of plastics is something like bend a material, bite a material, this is hardness, pull a material, or even it could be like heat a material. So finally, it's as simple like this. The problem, if you do it like that way, is that it is not measurable, it is not comparable, and at the end, it is not reliable. And that's why we need something else. And in the 1990s, we had the problem that in the world, all the people had different standards, doing different ways of specimen preparation, different ways of testing. So between the different regions in the world, we had no good comparability. And this is where the Campus group came in. So Campus means computer-aided material pre-selection by uniform standards. And this is a group of people from the material producers, the big producers of polymers in the world. And they found together and created new standards. And they have a strong influence even today on the whole range of ISO standards that we are working with today. So one of the main works they did is called The Contents of Campus, and the aim of this is comparability, produce comparability, and yeah. So it means this is comparable characteristic based on the same methods, based on the same specimen production parameters, and the same environmental conditions.
Okay.
So here I have a little slide for it,
yes.
just to show, and you also have an internet address where you can get more information about Campus Plastics.
Okay, thank you for that interesting background, Helmut. We can see that there's been a big partnership between the Campus group and the ISO organization relating to plastics then.
Yeah, this is true. David, maybe you can briefly explain to our participants what Zwicroll is doing in this field.
Oh, okay, yeah, well, Zwicroll has been producing testing equipment for polymers in Ulm in Germany for I guess more than 70 years, and of course we're recognized as a specialist and leader in this field, specifically because we have a strong industrial focus, and of course our customers are among the biggest petrochemical companies in the world. Our aim is to provide technically advanced products which help us to serve material producers, compounders, and the whole processing industry, where we have a high focus, particularly on the automotive industry, on medical applications. We also have a strong customer base in the testing service companies as well, and of course, not forgetting academia. And then to support our customers, we have sales and service organizations available all over the world, and they help to support our customers as they develop their own businesses around the globe. So Helmut, can you tell us a little bit more about the Zwicroll Polymer Lab? For example, could you give us some examples of the test methods that our machines have to perform?
Yes, David. I earlier mentioned already bite, bend, pull, and heat, and this is all what it is about. So let us start with bite. So Zwicroll offers nearly all type of hardness testing equipment for polymers. So this includes the Shaw meters. This includes different Rockwell scales like Rockwell K, L, M, E, R, and alpha, and we also offer IRHD durometers for rubber testing. So these hardness testers follow both the ASTM and the ISO standards. And yeah, this is about hardness. In the field of bend and pull, Zwickroll offers a large range of test equipment from creep to quasi-static testing, over fatigue, up to all kind of impact properties.
Okay, can you go into some more technical detail and maybe highlight some important benefits that our customers, maybe our listeners today, could look forward to?
Yeah, David. Let us start with creep. So in the this is a really important characteristic for a viscoelastic material, and the methods are ISO 899 part 1 and 2. This is ASTM D2990. But there are also many non-standard evaluations because this test is very current for R&D. So we offer a very standard creep equipment that we call the Kappa multi-station, and this is what you see here on the slide. It is a frame that contains 5 or 6 single stations. Each one is equipped with a load measurement and a precise electromechanical drive system which applies the required stress or strain levels. So each of these stations, which you can see here or also inside here on the slide, is controlled individually. The typical test types that we have here is tensile, is a flexural test, but you can also do compression test as you see it here on the side. These tests are very often run at ambient temperature, but we can use a temperature chamber like you see here if you want, and then run the creep test at any temperature in cold or in hot condition. So the strain measurement here in the creep is done by 5 video extensometers. These extensometers are installed at the rear side of the machine, so they look from the rear side to the specimen. And sure, the whole system is controlled by TestExpert 3 software, and this software also performs the evaluations, so it creates the test curves according to the selected standards.
Okay, Helmut, I don't know if it's yours, but my favorite topic is static testing, and I guess this must be the most common type of testing that people see in their labs. So I know you have some important things to share with us today on this topic. So could you explain, please, what tests are carried out and what have we done to make sure our customers, lab managers, and so on, to make sure they get reliable test results?
Yeah, yes, David. In static testing, we mainly see pull and bend. So means tensile test and flexural test. Even though there are additional tests, such, for example, compression or even shear testing. So you carry out these tensile tests according to ASTM D638 or ISO 527 Part 2, and the flexural test is D790 or ISO 178. So for such tests, in most of the cases, we can use a 10 kN load frame for that.
Okay, but for me, this is basic information, and I know there are a lot of different products available in the market. So I'm trying to figure out, thinking what our listeners want to know today is if they need to carry out tensile tests, what are the challenges they face, and how would they benefit from choosing a Zwick-Roll product? Can you give us a little bit more insight into that?
Yeah, the ISO standard pays very much attention to comparability. So, and here we see the influence of this campus group. So, for example, the requirements for the tensile modulus measurement are very tough and demanding to achieve. So customers must understand this, or they will just not get reliable test results as it's needed. So let me give one example. So first, for the tensile modulus, so this is a stress strain diagram. For the tensile modulus here in the first part of the curve, we need a constant and defined speed because we talk about viscoelastic material which are sensitive to the speed question. So in the standard, the speed is defined as being 1 millimeter per minute, and this is not defined as a crosshead speed. This is defined as a speed of the pulling clamp. So as an operator, as a user of a testing machine, we have to make sure that we really pull with this speed, and therefore we strongly recommend the use of parallel closing grips, so not to use wedge type grips where you lose a certain part of the movement. Now, so parallel closing grips such as pneumatic is really highly recommended here. Second, the tensile modulus in ISO is always measured between 0.05% and 0.25%. And this is whatever is the polymer. So this can be a fiber reinforced polyamide as well as a let's say low modulus polyethylene. So the common or the preferred specimen use a strain gauge, use a gauge length of 75 millimeter, and this means that the extensometer must be able to measure the difference between 37.5 micrometer and 187.5 millimeter with an accuracy of only 1.5 micrometer. Just for comparison, the diameter of a hair is 30 to 40 micrometers. So this is just a distance which is 3-4 times the diameter of a hair. So it's a very tiny thing. So with a 75 millimeter gauge length, we have this condition of accuracy of 1.5 micrometer for the difference here. And even worse, if you use the 1B type specimen in the ISO or the ASTM, we have only a gauge length of 50 millimeters. And here it would mean that our extensometer needs even to have an accuracy of ±1 micrometer in the measurement of the difference between these two limits. So you really need a very accurate extensometer for doing this. And by the way, this is something much more than only required by a class 1 in ISO or by a class B1 or B2 in ASTM. You have to respect the specific requirements which are described in Annex C of ISO 527 Part 1.
Thank you, Helmut. That's really interesting, and I'm sure people will be interested to check that out. And I wonder if maybe lab managers can check this for themselves. If they want to check their own extensometer specification, they could check the accuracy requirements simply by looking at the calibration certificate which they have in their lab. And in the example above, the calibration process must certify the extensometer. I could see that from a first calibration point of just 25 micrometers. And then, of course, you look at the difference between the points as explained in this Annex C. So it's really tough. Could I perhaps add here that anybody who's not really clear about their calibration status, they would be welcome, of course, to get in touch with us, and we could help them out. I think there are more points to think about here. I think that the same extensometer that has to measure these tiny strains should also be able to measure the yield point, right? At maybe something like, let's say 30% strain, and it should also work with no loss of accuracy, even if you're using it in a temperature chamber as well. So this is not easy, right?
Yes, Zwick has also offered high accuracy digital contact type extensometers for decades, as well as the latest non-contact extensometers, which are designed for ambient testing and below or above ambient. So these extensometers are fully automatic. They are rigidly mounted to the test machine load frame, and they do not need to be removed before the specimen breaks. So the reliability of test results is improved due to the automation and reduced operator manipulation. So these extensometers can easily be used to measure these 30% or more elongation. Today, many lab managers appreciate the benefit of these systems compared to traditional analog clip-on types, which are tricky to apply and often have to be removed before the specimen fails. So this is especially troublesome if you work with a temperature chamber. So our global customer have successfully used the mechanical extensometers MacroXtens that you see here on the right side, the multi-extens for decades. They are, let's say, reliable workhorses, often also used in fully robotized systems, fully robotized machines, which run day and night. And let's say they are something like the benchmark for other extensometer types.
Right, that's clear. So it's clear to me that the automated mechanical type of extensometers are a vast improvement compared to let's say that the traditional clip-on types that we all know from the past, both for improved accuracy and also for throughput as well, right? So whilst the test is running automatically, of course the operator could be doing some other tasks in the lab, and I know also from talking to people that that using non-contact extensometer systems. Would you say the non-contact systems that are available now are at the same level as the mechanical type? And for example, what is our current status of using that kind of technology?
Over the last years, the accuracy and functionality of these optical extensometers has improved a lot. So, for example, our latest VideoXtens HP is the first optical extensometer which achieves the same level of accuracy compared to the mechanical extensometers. So it fully conforms with the requirements for modulus measurement set by ISO 527. So here you see two slides. So the right side is a measurement curve done with a MacroXtens, so with a mechanical extensometer, and here on the left side we have a curve on the same material measured by an VideoXtens HP. And so you can see that this is very comparable quality of signal.
That's really interesting, and that means then I assume for the first time customers now have a choice of ways to measure strain according to their own individual test requirements, and probably also related to other ambient or maybe non-ambient tests they may have to do in their laboratory as well. I know a lot of labs are still using the older clip-on type extensometers, and the main advantage what I think the main advantage of these products is that they are, of course, much lower in price than more automated extensometry. Helmut, what advice do you have for someone listening today, for example, who may be trying to decide which technology they should go for?
Yep, David, you know we also have a complete set of high-resolution analog clip-on extensometers in our standard product range. This is not the problem, and this is for those customers who have a lower budget or for labs who just have a small numbers of such tests to be carried out. We also have digital clip-on extensometers, which offer the same advantages compared, or which offer some advantages compared to the analog technology. So both are fully adapted to measure tensile modulus, but the digital version combines a very high resolution with a very long travel of up to 40 millimeters and more. The advantage is that these use our digital technology to measure both tensile modulus and the yield point in the case of testing plastics. Yeah, maybe let me just talk about limitations. So the limitation of clip-ons is that they need to be manually attached to the specimen, and they have to be removed at a certain moment during the test when the machine is under load. So in case of brittle material, this may represent a risk for the operator, so it is better to avoid it and so not to work with these clip-on extensometers.
Okay, but are we overlooking an even bigger problem? So if the machine, for safety reasons, for example, has to be equipped with a locked or lockable safety door, safety shield, or is using a temperature chamber, then surely attaching and removing the extensometer before the specimen failure is really troublesome, and it must also be quite inefficient to spend so much time doing that and caring for safety during the test.
Yeah, our customers look for much better solutions, and so we have developed products to help them to be more efficient. Using our macro extents or our video extents, remove all these inconveniences and improve faster throughput and better reproducibility.
Right. So, Helmut, we've mentioned temperature chambers now, and I think this is another interesting topic to move towards, perhaps to discuss a little bit more. The process of mechanical testing inside a temperature chamber hasn't really changed that much for many years, I think. So these technically quite simple, what can I call them, heated or cooled cabinets, they're often difficult to set up. They have different control systems, control electronics and buttons to push and so on. They can be quite time consuming to operate. Associated with that, I guess it must be difficult to control the traceability of the temperature control parameters, the temperature data recorded during the test. This, in some cases, probably not even possible, and must contribute to reduced reliability of test results. Why do you think this technology has not changed for many, many years?
Yes, the temperature is really another interesting topics. So, some years ago, after consulting with our customers, we developed a range of our own temperature chambers, which are totally integrated into the test machine technology. And we have optimized the workflows to help the user to achieve better results. Let me just highlight a few benefits which give customers many advantages for our in combination with our static and dynamic testing machines. So, as I mentioned, there is a full integration. And this full integration concerns, for example, our optical and also the non-contact extensometers, which are, as you can see here, rigidly mounted to the load frame, and we measure here through a side slot. So this is always part of our temperature chambers. You can also see it here in this picture in the center. So there is a slot or a slit, and either you can have a window pane here in order to make to measure with an optical extensometer, or you could also have just some clappets, so then you can also use it with our mechanical extensometer. Another, let's say, real advantage of this slot at the side is that it allows, or it gives the operator free view to the test specimen here by the front panel. So there is a, let's say, for some of the extensometers, there is a specific mounting of the extensometer, which moves it at half of the crosshead speed. So this ensures at the end of the day a better use of the available field of view, and by this very reliable measurements over a long range. So we can also automatically control by the TestExpert software the speed of the fan from the during the test. So one advantage of this is to reduce vibrations which may come from air circulations, and so avoiding this means to have a calmer environment, which is important, especially during the measurement phase, the modulus. So another point is our customers wanted to avoid opening the big door that you see here in the front of the temperature chamber, as you lose all the cold if you open it, and it let's say increases your consumption of liquid nitrogen. So what we developed here is a door-in-door system, and this allows to the operator to access the grips or the test area just by a small clapet. So this improves, you don't lose the liquid nitrogen or the nitrogen in the chamber, so you don't lose the cold. And another advantage is you don't bring in so much moisture, so the build-up of ice is also very much reduced. So what else do we have here? We have this magazine. This is an intermediate magazine. So what you can do is you put your specimen into this magazine, which is in the chamber, so to precondition it for a certain time, and then you can just take the new specimen here from the magazine and put a fresh specimen into it again. So you create a running process where all your test specimen have the same state of conditioning. So all these benefits allow our customers to achieve a greater throughput while being more efficient and environmentally friendly, and of course helping them to get more reliable test results.
That's excellent, thank you. Helmut, Zwickrol is probably famous for being, I guess, the first company to sell a multi-station computer-controlled robotic test systems, and these were way back in the 1980s. You and I probably remember those days very well. We were around in the company then. So since then, we've sold hundreds of these automated and robotic test systems. Can you share a little bit of your knowledge about how those systems have developed over the decades?
Yes, David, I really can remember those times very well. Um, they were being used all over the world already when I joined the company in 1987. So over the
Right.
years, those systems have been continuously developed, and we offer automation products for many, many types of tests. Quasi-static like Tensor and Fletcher have become very standard for automation. But we also robotize other test types where large numbers of specimens are typical. For example, impact test, Sharpie, ISOT, or multi-axial. So I would say automation has become more and more flexible over the years. And our newest product here is what we call the Robotest N. So this is a very flexible version of a robot which can be adapted to different test method and different handling requirements in a quite easy way and without, let's say, without much specific knowledge about robotization. Did you know that in polymer testing we have robotized many R&D labs where large numbers of tests are required in the field of, for example, of compound development? So it is not only production testing which demands for such systems. One big advantage of the robotized testing system is that it reduces the statistical scatter of the results. This is like having only one operator exactly doing the same thing all the time. So this is surely quite important for those who generate data sheets or materials data sheet for their material.
You know, I'm always fascinated to see these robotic systems being used around the world. The speed that they operate, the reproducibility is always impressive to see, and it makes life so much easier for test labs. I know customers who've been using these systems for, as we said already, more than 30 years, and I know that they would never return to a manual kind of testing after that. Howard, have you got any other examples of test methods which are used in the plastics industry? Something we might not have talked about so far?
Yeah, let us briefly talk about fatigue testing. So compared to other materials and especially compared to metals, there's much less fatigue testing with plastics. Most of the fatigue testing is performed within R&D labs. So we develop and produce servo hydraulic testing machines as well as the LTN, which is an electrodynamic testing machine. So I show you the LTN is interesting for let's say for the low force level, which is typically needed for polymers. So it goes up to 10 kilonewton of load, and it works with an electromechanical drive that you see here on the top of the machine. And this drive system produces oscillation frequencies of up to 100 hertz. So this is much more than what is typically needed. Polymers are maybe tested at 3, 4, 5 hertz. 10 hertz is already a lot because you have the problem of heating the material, which would damage the results. So typically we use it as at quite low oscillation speed. So this machine, for example, can be used for classical fatigue tests, you know, SN curve or Wöhler curves, you may call it. We use it for the crack round bar test, which is a specific test in the world of material grades for PE pipes, polyethylene pipes. The big advantage of such machine compared to servo-hydraulic is that it has a much lower running cost. It makes much less noise in the lab. And one big advantage is it is completely free of oil and oil fumes and so on, which is a typical problem with servo-hydraulic systems. So at the same time, such an LTM machine provides a very high response, so it's a very reactive machine, good accuracy, and many possibilities of the control of the piston movements.
Right. The next part I'd like to go into is if we think about a typical polymer test lab, I assume we would see in that lab different types of impact, maybe high-speed testing machines. Could you share a little bit of your experience about these types of testing machines, Helmut?
Yeah, so the most standard method is a pendulum impact tester, as you can see here. ISTM typically use the ISOT method, while the ISO standard can work with both. There's a standard for Sharpie testing, you see here, or for ISOT testing as well. And you may have this in notched version, like you have in the ASTM, but in ISO we also have unnotched specimen. Unnotched specimen. There is a complete product range here of let's say conventional pendulum impact testers working with a drop height, so measuring energy from the drop height, and also for instrumented versions that work with a load measurement. So here, for example, we have a small version which is only 5 joule. This is typical for people doing notched impact tests within the ISO standard, so Sharpie tests typically. Then we have a more universal version in 5.5 joule, in 25 joule, or with 50 joule capacity. So universal because these machines can do all Sharpie, ISO, tensile impact, and Günster testing, so all typical methods, and this also in the world of ASTM or in the world of ISO standards. Yeah. So
yeah, I noticed you, if I could interrupt there a little bit, I noticed you referred to an instrumented pendulum impact tester. Can you give us a little bit more information about this system and what it can do?
Yeah, instrumentation finally means the measurement of force during the test. So instead of just having an energy single point value, if you want, you have here integrated into the hammer this load measurement system. So it's a very, very fast measurement system. We go here with a data acquisition speed of up to 4 megahertz. And this allows us in the first step to produce a force time diagram with a very high resolution. So this is a typical diagram, and this diagram then can be converted by Newton's law to a force deflection diagram. So we see force and deflection, so force and deformation. And this is very interesting for example, for quality control labs, because by the shape of the curve, we can identify the type of brake. We can identify the type of brake, so the customer does not need to, or the operator does not need to look at this anymore and to decide which kind of brake it is. And the working principle here of this machine, or let's say another advantage, is you don't need to change the hammer so often. So in a conventional impact tester, you always have to adapt the hammer size to the level of energy you want to measure. While here in an instrumented machine, you can use the biggest hammer possible. So you can use a 50 joule hammer, as your result does not depend on this potentially available energy. You just measure the forces. So, and this is the main difference. So these machines do not anymore measure energy, they measure forces, and if you want, forces in time and elongations. And so this is a very interesting way, and you can obtain a lot of information from this test. For example, as I said, the automatic recognition of the brake type. You could also find here supplementary information about the deformation, force deformation curve, or you could also measure fracture mechanic properties. So this is all about the instrumentation in pendulum impact. We also have drop weight testers, and these drop weight testers are, let's say, basically designed for doing multi-axial impact tests. This is ASTM D3763 or ISO 6603 part 2, and so these drop weight testers have a typical range of speed between 2 and 8 meters per second. They can go faster if you work here with an acceleration. So then you can go up to 18, 90, 20 meters per second. And we also produce servo-hydraulic high-speed testing machines, and these high-speed testing machines are often used, for example, for tensile testing, and then they can go from nearly quasi-static up to 20 meters per second.
Right. Helmut, there's one more topic I think we should talk a little bit about today, and that's MFR. What products have we got to handle that kind of testing?
Yeah, you know, we have developed a complete range of melt flow plastometers, and it covers, let's say, all different situations that we find in the market. So it starts from a very basic instrument. We call it the C-flow, the compact flow, which is just able to measure melt flow rate by cutting in constant time intervals and by weighting the extrudates. You have this mid-range machine, we call it the M-flow or the modular flow, and this is, yeah, as it says, very modular. It can have a travel transducer, so it allows you to measure melt volume rates. It allows you also to control the whole test procedure automatically, so that the operator can switch on the test and just turn around, and the whole measurement procedure is automatic. If you measure different type of material, or for example polyethylene with different weight sets, you can have such a weight pre-selection unit where all the test weights stay in the machine. And this also has a big advantage in terms of safety, because you don't need to handle these weight pieces any further. Yeah, and then we have, let's say, a little bit the flagship here is we call it the A-flow. It's a fully automatic machine. It works a little bit like a rheometer, so it has an electromechanical drive and a load measurement, and it can, let's say, work up to 50 kilogram. This is interesting for pre-compacting. This is interesting also sometimes for measuring, let's say, very sticky material. And this is interesting to chase out the remaining material at the end of the test. And you see here two different units. So one is the measurement unit, which is this one, and the other one is a cleaning unit. So we can also automate the cleaning. Let us have a little look to a video that I have here. So it shows the lady how it operates the machine. So I just switch on the video and you will see how easy it turns. So this is one of the big disadvantages, it's really easy to handle. So this is the measurement piston going into position. We control the whole test by a curve. You see here a cutter. At the side, you also see a die plug. And at the end of the test, you see the results. I know this film was a little bit fast, therefore I will just show it once again. So you see the handling, the lady turns it from the cleaning position to the testing position. We see the curve here. We see the extrudate cutter if you want to do MFR or use the die plug. These two are connected to each other and you have a complete ready-made result table. Sure, you can also connect the M flows and the A flows to our test expert, and then you have the whole control of the machine on the PC by the PC software. And this PC software also allows you to connect up to 6 units to only one PC. Yeah, David,
Okay.
this thing is really, let's say, designed for quality control.
Right.
And let's say these A flows, a typical use is it runs 24 hours a day and it runs nearly 365 days in a year.
Excellent. Helmut, thank you very much for sharing your long time experience with us today. I hope everybody got something interesting and they learned something out of that. Maybe I could just spend a couple of seconds to summarize some important points which I took out of the discussion today. So the one thing I think for people to keep in mind is that with Zwickroll, we're supplying a complete mechanical test lab for plastics. And of course, we welcome discussions with customers to discuss their individual testing needs, everything they want to know about testing applications and so on. They just need to get in touch with us either in the headquarters or via their local sales organization. Second point, I think, which is important, is that all the machines you described and explained so well today, Helmut, are running on a single software. And I think it's important to say that this is the Test Expert 3 software platform. And there are some advantages to that, of course, which means it allows for the same operation, whichever test you're performing, whatever level of automation you're running at, you're always using Test Expert there. I think it also gives customers a lot of advantage, not only for supporting and providing service for customers, but also for customers to have a common user interface, and that can make the operation of the machine much easier, and it can also reduce the cost of training of operators in a company. Another point is that it means the same interface connections can be used if you have to transfer test data to, let's say, to a LIMS or a laboratory information management system, or any kind of data storage systems, databases, data handling in general. So you've got a common interface there, so it means you can have standardized interconnections across not only a site, but across global sites as well. I think the last point I want to mention is regarding the Extensometer, as we talked about near the beginning of the webinar. I think it's interesting for customers now that they really have a choice a good choice of contact, non-contact, extensometry, which means they can really ensure that they meet the tensile modulus requirements of ISO 527. So those are the points I took out to today. So once again, thank you, Helmut, for your good insight into the plastics industry. And thank you also to me as well for the participants for listening today.